I'm trying to shut it down.
Serious, huh? Okay. So in the 70s, the first real concrete demonstration that dark matter really existed was studying the rotation curves of galaxies. And although at the time most people didn't like the idea of dark matter, certainly not astronomers didn't like the idea of dark matter explaining the rotation curves of galaxies, was amazed to realize that they actually got pretty much the right number for the relative density of dark matter today, that we now know is the right answer today. And it took many years of subsequent observations in many different areas, looking at the CMB, galaxy surveys, study of large-scale structure, both matching on the galaxy surveys and big computer simulations, strong and weak lensing, the bullet cluster that proved that this was not due to some modification of Newtonian gravity, but it really was due to dark matter. So there's so much evidence eventually piled up that it was unescapable that dark matter exists, and it's about 60. The latest result from Planck, 26.8% of the energy density of the universe. That's pretty close to that number, which I thought was pretty exciting. However, all the evidence we have is gravitational, so it's quite likely, quite possible that this matter, whatever it is, and it is matter, only interacts with us through gravity, and these are all the observable ways we'll ever see. And that's kind of disappointing. But if you take that point of view, and then you look at the numbers, there are some coincidences that come up, and I'll go through those coincidences that lead people to think maybe dark matter plays with ordinary standard model matter in some way other than gravity, and so then that leaves an opening for model builders, and of course they took great advantage of it. Here's a nice diagram made by Tim Tate last year for the U.S.'s long-range planning process, and he tried to make a summary graph of all of the dark matter model building out there, and there's a lot. Luckily, we talked about this today, so I don't have to talk about it. We heard a lot, so I won't talk about this. I had some slides, but I took them out because the slides everybody else had was so much better. And what I'm going to talk about is what's in this tiny little corner here, which is pretty much all of the composite dark matter models. And you see theorists, most model builders like to work in perturbative calculable theories models, and so most of their models live around here. That's why they get so much space. Okay, now the first big hint was noted by Shmuel-Nusinoff back in 1985, and he was thinking about dark matter. And also at the time, Technicolor had just sort of been invented, and it was very popular. People hadn't realized it yet that it was going to happen. Maybe they did, but it still was popular then. But at the time, astronomers still hadn't figured out how much normal matter there is in the universe. That was a big, long-standing problem. There's a lot of dark baryons around, not dark, but baryons hidden in hydrogen gas and things like that. It took a long time for people to figure out that this number was not 0.01, but 0.05, much bigger. But in those days, he said, he looked at these numbers and he said, well, there's a curious thing. We know that the number of baryons is highly sensitive to baryogenesis, and it has to do with this matter-antimatter asymmetry, and this number is very model-dependent, very sensitive, and it's 10 to the minus 9. But he says, well, let's say, dark matter was in thermal equilibrium with the universe, and so there ends up being a number density about as much dark matter around as there are photons around, no matter-antimatter asymmetry there. Then if you form this combination, it's only 0.01. It could have been 10 orders of magnitude different. Why are these numbers so close to each other? And then he said, well, if dark matter participates in baryogenesis some way, so that its relic density is also set through some kind of baryogenesis mechanism, so there's a dark matter, dark antimatter asymmetry, And then so you could say, well, this ratio is the right thing that I should be comparing. And this would work great because back in 1985, Technicolor, you thought that technibaryons were a TV, normal baryons are a GV, so that's a 10 to the minus 3 ratio. It wouldn't be that surprising if, you know, in the model building details you could get matter-antimatter asymmetry only differ by a factor of 10 between baryons and dark matter. You know, so that was, he said, this is great. This is the explanation. Technibaryons could be the dark matter. Now the problem is that, you know, since that time there's been a lot of evolution in our understanding of dark matter and normal matter in the universe. So now we know today that the amount of dark matter is only about 5 times more than the amount of baryons. And so this now goes under the name asymmetric dark matter, and this solution is called the light solution of the asymmetric dark matter, and people are out looking for 5GeV type candidates. But this is not great for Technicolor because this is way too light. Okay. However, Barr, Chivukula, and Farhi pointed out a few years later that Technicolor and a model like Technicolor is a little bit complicated because Technicolor has its own finite temperature phase transition, and that temperature is presumably slightly higher than the electroweak temperature. Also, you know, Technicolor, the mass is heavy relative to where the sphaler mechanism is supposed to be working. So you can't really assume that all of the techniquarks and everything are not bound yet into hadrons and they're basically behaving relativistically. Instead, you have to take into account the fact that by the time the sphaler process is turning on, the techniquarks are all confined into their technibaryons, and they're heavy, and so there's going to be Boltzmann factor suppression, and so they worked it out, and it's some factor like this. And so now there's 2 possible solutions to a dark matter candidate like technibaryon, which is, one, it can be really light, around 5 GeV, or you can have an asymmetric particle, dark matter particle, which is heavy around 3 TeV. And it turns out that this is perfect for Technicolor. So, or anything like that where you have TeV scale dark matter that participates in electroweak symmetry breaking. So, this is great, but the real problem is to try and use this as a way to constrain or rule out a dark matter candidate is very challenging because the details are very sensitive to exactly how you build the interaction of your new dark matter sector with the standard model and how it participates in the electroweak sphaler process, given that your new sector also is likely to be going through a phase transition somewhere around the same scale. So it's very complicated. But let me show you at least the state of the art for how you would go about it. This is the calculation by D'Onofrio, Rumakainen, and Tramberg, the best to date. What they do is they start from the electroweak standard model, no QCD, but everything else. And then they use a dimensionally reduced system, which you expect to be good in the high temperature limit, and that matches onto this 3-dimensional gauged Higgs system. And then this is what they study on the lattice. And of course, all the couplings, the gauge coupling, the mass, the lambda, they're all determined by matching onto the 4-dimensional theory. But in this system, they can then try and first locate the temperature where the Higgs starts getting its Phys. So you can see it right here. It's around 160 GeV. And then as the system cools and the Higgs valve starts turning on, the Higgs field starts Higgsing the gauge field. And what happens then is this is the sphaler rate. And this is basically the topological susceptibility, but in 3D, so it's related to the Chern-Simons number. But it's basically looking at how the topological susceptibility dies as the gauge field gets Higgsed by the Higgs. So the Higgs valve is turning on, and the susceptibility is dying as a result because the gauge fields are getting Higgsed. And so measuring this slope, that's the thing you need to figure it out. So it's beautiful to the extent that we trust this dimensional reduction. But what the downside is that now that we know this slope, we know that baryogenesis doesn't work in the standard model. We have to add something to the standard model to get baryogenesis to work. Because we don't produce the right amount of matter-antimatter asymmetry with just this result. So if you wanted to do the same thing with the BSM theory, you have to start back at the beginning. You have to start with your electroweak theory plus whatever BSM physics is. Then you have to figure out how to dimensionally reduce it down to some system like this, which is probably not going to be just this system. But particularly if it's something like Technicolor, you're going to have this gauge group plus probably a Technicolor gauge group, and you're going to have to deal with the fact that they go through finite temperature phase transitions at different points. So it'll be a bit complicated. Okay, and nobody's ever tried it. All right. Okay, but let me finish hint number one. All that said, it looks promising to consider the possibility of maybe there's an asymmetric dark matter that participates in electroweak symmetry breaking and this fail-around mechanism, and so there's all sorts of models to look at that. Okay, including Technicolor-like models. All right, now let me go to the next hint that suggested that maybe something important is happening in the dark matter sector. And that is thinking about maybe the dark matter doesn't come about as some asymmetric remnant of the baryogenesis process, but in fact it doesn't participate in baryogenesis at all, and its relative abundance is just set by its ability to annihilate into standard model particles through some kind of 2-to-2 interaction. And so you do that, and you come up with this kind of formula, the basic idea when they first wrote it down, and I got these out of this paper. And so what you see is that this is the velocity average to annihilation cross-section, and you model that through some kind of dark disk approximation where you basically say it's basically proportional to 1 over the mass of the particle. And you put it in the astronomer units or whatever, and this is at that time, that was their estimate of what the dark matter mass was, and you get some formula like this. This number we know from experiment. And so this is the thing that we want to find out. And the important thing to realize is if you plug in all these numbers and then you say what value of alpha do you have to get the right relic abundance, assuming that the mass scale is around 100 GeV, and you get something that's like of order 0.01, it's just right in the ballpark for being a nice perturbative electroweak cross-section. So everybody said, oh my gosh, it's a miracle. And so then the WIMP miracle was born. Unfortunately, we've now had lots of decades of direct detection experiments, and most of the models of WIMPs that people put out there generically have already been ruled out. I mean, now you have to be very careful about your WIMP model building because you have a lot of constraints from the LHC to evade, and now you have a lot of constraints from dark matter direct detection experiments like LUX, which I'll show in a minute, to evade. So it's very hard now to make a successful model of WIMP dark matter. However, the basic idea of thermal freeze-out is fine. You didn't have to choose the electroweak scale. Now let me show you another example. If you instead said, let's say I have some dark matter candidate, it's basically a scaled up version of QCD. So there's some QCD, the equivalent of a QCD neutron flying around, and that's the dark matter. Well, then you just look up the cross-section for n and bar annihilation, and you figure out what it is relative to the neutron mass, and you get that alpha is about 16. And so then you plug it into this formula, and you say, well, if that thing, that dark neutron is going to be the dark matter, then it has to have a mass of about 300 TeV for it to freeze out at the right relic density. Now, some people say, aha, this is an argument why this wouldn't work for Technicolor, because if you had something that was Technicolor, but your Technicolor thing didn't really participate in the electroweak fail-around process, then it can't be the dark matter. Yeah, that's right, but that's okay, because let's look at this formula again. The spin average, the velocity average cross-section goes in the denominator here. So if I imagine, stick in whatever mass you want, hold the mass scale fixed. As I dial up alpha, my fraction of the relic density goes down. So and that makes sense. As the interaction, the annihilation cross-section increases, you get less stuff. Okay, so having a scaled up QCD like dark neutron sitting at the TeV scale is fine from the dark matter point of view. You'll just never see it because it's an insignificant fraction of the relic density. If you want it to be a significant fraction of the relic density, it has to be up around 300 TeV because the annihilation cross-section is so big. So anything with a strongly interacting, a big annihilation cross-section, if it's going to be part of the relic density, a significant fraction of the relic density has to be heavy. Okay. All right, so let's see. There's one other hint, very recent. So, with the success of CMB in large-scale structure and lambda CDM cosmology, everybody said great, and all these simulations were able to reproduce the large-scale structure and the filaments and all of that. So they then kept pushing the simulations down to shorter and shorter distance scales until they got to relatively small galaxy clusters and even individual galaxies and their local dwarf galaxies. And they started to run into a lot of problems that the dark matter models were not reproducing what was seen in nature. So there's the names of these problems are the fact that bulge-less disk galaxies exist, whereas in a dark matter-driven galaxy formation, you expect there's a big cusp of dark matter because it doesn't interact in the lambda CDM model. So there's a lot of really dense region of dark matter in the middle, and then the baryons should get trapped in that, and there should be a bulge. And yet they find galaxies without bulges. So they don't know how that could happen. This is a related cusp core problem. The cusp core problem is you think dark matter is really cuspy because there's there's no self-interaction of the dark matter to give it a reason to smooth out the cusp at the middle. And yet the cores don't match the profile the core of the baryons in the center of the galaxy don't match the profile that you would get from so somehow even in dark matter phenomenology, they have, by ad hoc, put in some term to sort of smooth out the cusp, even though nobody really knows exactly what physics would give rise to that smoothing out the cusp. But even that doesn't really sort of solve the problem. So this too big to fail, this is, I don't know, the name is a little bit complicated to explain. Basically, what it is a similar kind of thing. You expect that if you're going to have dwarf galaxies, when the dark matter formed, there should be, let me make sure I get it right. There should be lots of bigger dwarf galaxies closer in than what's observed. And there should also be a lot of even littler dwarf galaxies further out. And what they don't see is they don't see enough dwarf galaxies of the right sizes to match the expected amount of dark matter in those dwarf galaxies given the size of the expected dark matter halo in the big galaxy. And so, and then there's also missing satellites. This is related to missing, you don't have enough small galaxies flying around the big galaxies. So one of the solutions that was proposed to solve this is to maybe dark matter has some self-interaction, and that's going to smooth out the halo, and that's also going to make it easier for dark matter clumps that seed the formation of dwarf galaxies because the potential well is not so deep. If the dark matter can interact with each other, it can escape. And so then the dwarf galaxies will be smaller, and there will be fewer of those even smaller dwarf galaxies. So it's an interesting idea, and they came up, but there's the counterexample that if you look at the bullet cluster, which was two galaxies passing through each other, the best fit was dark matter that was almost had no self-interaction. The one thing that's different is the velocity scales didn't match up. The bullet cluster sort of puts limits on the self-interaction cross-section at the velocity scales around this, whereas for the stuff that's relevant for galaxies is at an order of magnitude lower velocity scale. So this was a way of trying to understand how to solve the galaxy problem, but still be consistent with lambda CDM cosmology and with the bullet cluster result. However, when I first heard about this, I was like, great. This is like study galaxy formation and learn something about particle physics. But then I started translating these astronomer numbers that I could not understand into the natural units, which I know how to understand. And then, surprisingly, it basically says, well, given this cross-section, and let's say a cross-section of order 1 over the mass of the particle, and maybe there's some coupling in there. If it's a weakly coupled particle, you can maybe get the ratio of the cross-section to the mass of order 10 MeV. But if it's a nice proton-like particle, then you can get masses right around 1 GeV. So it seemed really surprising to me that you're doing astrophysical simulations of galaxy formation, and your main ingredient is non-interacting dark matter. You assume the baryons aren't doing anything, they're just there along for the ride. Then you look at the results and you compare them to nature and you say, it isn't quite right. What I really need is a particle that weighs about 1 GeV and has an interaction cross-section right about the interaction cross-section of a proton. So why not just put protons into your simulation and see if that fixes the problem, instead of trying to say dark matter has to have a self-interaction cross-section. And so, in fact, this is what's now happening. People are starting to add dark matter plus baryons into their galaxy formulation simulations, and they see differences that might account for this, but it's very much a work in progress. But remember, there still is that asymmetric dark matter candidate, the light solution around 5 GeV, so you can have both things going on. So one question is, will the simulations / observation in the astrophysics community become good enough that they can actually distinguish how many different kinds of particles that have order GeV masses and order proton scale scattering cross sections are participating? Like, could we have a dark matter component and a baryonic component? I don't know, but there's a lot of work to do there. So I would say for model building, it's probably a little bit too soon to chase this particular ambulance. Okay. All right, now these are all the hints that lead the model builders to want to build models of dark matter. Let me give a bit of warning. If you want to do something with your dark matter model and have it just be massive and talk to gravity, you have a lot of serious constraints to have to deal with. The Lett basically looked at E plus E minus goes to any new charged particles. They didn't see any, and so that sets a mass of 90 GeV and anything that can be produced through E plus E minus. Also, Z exchange has been ruled out for a really long time. Somehow I didn't get up. This is 10 to the minus 46. If you have any way of communicating with the standard model through single Z exchange, 2Z exchange is okay, but single Z exchange is disaster. Higgs exchange was for a long time the way out, and so that's the way most SUSY particles, for example, talk to the standard model. Except the lattice calculations of the sigma terms in nuclei have gotten a lot better. And also the results from the direct detection experiments like Lux and Xenon have gotten a lot better. And so now you have to do some very serious model building to somehow keep your dark matter candidate alive and have it not be observed. So you have to find some way to sort of suppress the natural Higgs exchange cross-section that you would expect. And pretty soon, in 5 years' time, if we don't see dark matter, I think Higgs, weak scale WIMPs, thermal relics will be ruled out. Okay, if you want to try to build a particle with this light asymmetric dark matter, it's really quite challenging because, let's say, a typical example, let's say you wanted the pi zero, its isospin or G parity would protect it as a quantum number, so it'd be a nice stable particle, it couldn't decay to anything. That could be your dark matter candidate. Yeah, except for the fact that the pi zero, it has partners, the pi plus and the pi minus, and they would also be stable, and they're also charged, so Lett would have produced them. So you could say, well, maybe I have a model, and people would write this model, where the pi zero is 5 GeV, and the pi plus and minus are like 5 TeV. I want you to try to imagine how I'm going to split the pi and multiply it by that kind of scale, but that people try to write down that kind of model. It looks really fine-tuned. So this is kind of crazy. One popular approach for this is glue balls, but then you say, well, I have a glue ball. Okay, that's easy. It's the lightest glue ball is 5 GeV, but now how am I going to couple it to the standard model? Well, usually you say, well, I have S squared for my pure glue action for the glue ball. Maybe I make some higher dimensional operator, F squared of this with F squared of electromagnetism. Well, that's dimension 8. So it's really kind of sounds a bit unnatural to say I have these two sectors and they only talk to each other through some dimension 8 interactions. But that's the style. Okay, so now I'm going to start focusing on composite dark matter candidates that are made out of fermions. The fermions do talk to the standard model. They're charged under the standard model some way, and that allows us to talk to the standard model. But those fermions are confined into hadrons, and the hadrons are standard model singlets. And then the nice part about that is because they're standard model singlets, they basically have no dimension 4 and lower interactions. However, we know from neutrons, the neutron has electric form factors, etc. So you can have a magnetic moment, you can have a charge radius interaction, and then these things you can get rid of if you impose some kind of flavor symmetry. They would be true in QCD if we set the right combinations of up and down quark masses. However, you can never get rid of polarizability. So there's always a possibility that 2 photon interactions are allowed. Presumably 2 Z interactions are allowed too, but those are much higher suppressed. Okay, so there was a nice summary at the Lattice conference of all the different models that have been looked at. I expect we'll hear about some of these later today, after me, and so I'm not going to, I'll just talk about the ones, I'll talk about, let's say, this SU3, SU4 4 flavor, and these various SU3 ones. Okay. Great, and so most of the work that I'll present, calculations were done by my collaboration, and in particular, the people who did a lot of the real hard work are these Mike Bukoff and Enrico Rinaldi, and Livermore, Ethan Neal, and Sergey, who, well, I don't know where Sergey is now, and Graham Cripps is in Ohio, Oregon. Okay. Now, the first calculation we did was say, all right, let's imagine we have something like a QCD baryon. Now, it's not Technicolor, so it's not coupled to the electroweak theory in any way that will break electroweak symmetry. Instead, what we wanted to do was just give, and so you can see that in particular, they're SU2 left weak singlets. That way they won't break electroweak symmetry. This is a bit of a problem because this model, this is not a complete model, the way we've written it down, the pions won't decay. So you'd have a bunch of pions running around too. Using the electroweak coupling as a way to allow the pions to decay by going through a W is really nice, but then you have to be careful that you don't break electroweak symmetry. So I'll show a better example of that when I talk about the next model, but there are ways that you could get around this. I mean, some model builder would just say, oh, well, there's some W prime, and I add a W prime, it's heavy, and it does the job for me. But we're not really interested in that model building game. We're the Lattice group. So what we did is we calculated both the magnetic moment and the charge radius in this case, for 2 different number of flavors, 2 flavors and 6 flavors. This uses domain wall fermions. And of course, it makes sense that the magnetic moment, being a dimension 5 interaction, is the dominant interaction. And at the time we did this calculation, Xenon 100 was the best limit, and you can see that it was about 10 TeV was the limit on dark matter that you could get from something like this. So then, again, that means that anything from 10 TeV up is probably allowed for over a huge range of masses. But again, at 10 TeV, if you have something where it's proton-like, so the quarks are really light, and they're bound into a really heavy object, that's going to have a big scattering cross-section, so the relic density would be really small. What would you need to do to make it be the real dark matter? Well, you'd imagine that this baryon was made of actually very heavy quarks, and so that most of the mass of the baryon was concentrated in the heavy quarks, and then the annihilation cross-section would be a lot closer to this dark disk approximation of 1 over the mass squared. And so we imagine there's a knob in this model. You think of it as the ratio of the quark mass to the confinement scale or something like that. It's how much of the mass is concentrated in the quarks, the valence quarks, and how much of the mass is concentrated in the glue that binds it together. And the more mass you concentrate into point-like quarks, the smaller the annihilation cross-section becomes, and then the lower the higher the relic density becomes at a low mass. Okay. However, this is these. Let me see what I have next. This came out. I mean, well, first we were up here, and then this kept going down. They're now a factor of 10 down in cross-section below where xenon was when we published. So this is really pushing on this result a lot. It's pushing the mass up. The mass, now we're in the sort of getting close to 100 TeV range where the allowed region is for a mass of this particle. Let me show it here. So this again is another one of these summaries from the Snowmass. Here was the xenon result at the time. Here's the latest Lutz result is here. You can see it's really cutting into this dark baryon space, getting you somewhere in the 50 to 100 TeV range. And ultimately, here's the next generation experiment. Lutz just finished running so that they could take it apart and build LZ. LZ will really push this whole dark baryon area, probably rule it out. The interesting thing is this line here, maybe you've heard of it, maybe you haven't. It's something called greased Kamienowski partial unitarity bound. What's that? Okay. So Greased and Kamienowski noted that if you say I have a thermal relic and here's this thing, how big can the scattering cross-section be before you start running into a problem with it being a thermal relic? And so it's pretty simple. Partial wave unitarity has been used a lot in the past for people who do partial wave analysis. But it really assumes its properties of the unitarity of the S matrix, but it really only assumes 2 to 2 scattering. Of course, now, these days, Lattice QCD theorists are becoming real experts in scattering theory, so you know that when you have 2 to n scattering, that you can't really use the S matrix approximation, that now gets a lot more complicated. And so you can't use this argument anymore, but let me go quickly through it. It basically says that the maximum cross-section you can get is somehow related to the energy. You can compute the energy in this very simple way. The average energy is something like the dark matter particle times its velocity, and then there's an angular momentum factor. So this is the total cross-section in each angular momentum sector. In their case, they only needed to use J equals 0. And then you can see if I plug this into here, I'm going to get a solution where as I increase the mass, at some point the relic density will grow bigger than the observed relic density, and so that will set the limit. Where is that? It's around 300 TeV. And so they say, well, there's no way a particle can be a thermal relic and be heavier than 300 TeV. The only problem with this argument is that it relies on 2 to 2 scattering. We know in NM bar annihilation that the branching ratio of NM bar to 3 pions is about 10 times the branching ratio of NM bar to 2 pions. So unfortunately, this argument doesn't hold exactly for the case of dark baryons. Okay. However, it doesn't really matter. I mean, the ultimate limit on LZ is really going to push way beyond 300 TeV. Okay. Let's see. Good, I got that. Okay, so now let's talk about stealth dark matter. One of the dark baryon that we had before was a dark composite fermion. Now I want to talk about one way to get rid of the magnetic moment is to say, let's not have a dark fermion, let's have a dark boson, a composite dark boson. That's easy to do. You just use an even number of colors. Now you have an even number of quarks going in, so it makes a nice boson instead of a fermion. just the fact that it's a boson kills off the magnetic moment. Then it's easy to get rid of the charge radius by giving it a flavor symmetry so that you don't have a charge radius to have to deal with. And then you're left with something which is a nice neutral thing that only interacts through the polarizability. Now, in this model, we also wanted to make sure that we coupled it to the electroweak part of the standard model just enough to be able to get all of the pions to decay that was generated in the early universe to decay by now. So you need to give it a very small coupling to the standard model. But we did check that it doesn't screw up vacuum alignment, so it doesn't work like Technicolor. Also, it does make an insignificant contribution to things like the S parameter, so it's not really observable in that way. It also means that our quarks will get a slight little contribution from the Higgs to their mass. So in this model, we have we could, in principle, have our quarks in this dark quarks in this model get all their mass from the Higgs, but then we would be ruled out by Higgs exchange in direct detection. So we also add vector-like mass terms and then chiral mass terms, so that like Higgs Yukawa type interactions. And so there's a little bit of fun model building that you can do in the interplay between those different sources of masses for the quarks. Here's, I guess, the spectrum, something like that. And you can control the splitting either by varying the Yukawa couplings or by varying the, what we call up and down quark masses here. But this allows you to basically dial the Higgs coupling to be whatever you want. So we always dial it so that the dominant interaction is polarizability, and yet we always want the Higgs, the interaction with the standard model to be big enough so that there are no dark pions running around. Okay, good, and you can read the details in these three papers. All right, so here's our calculation of the polarizability using the background field method pioneered by Will Detmold and his collaborators. We found, well, we can do this calculation pretty well. The big uncertainty is actually this uncertainty in nuclear matrix elements. This is exactly the same problem that faces the Majoran and neutrino experiments that try to look for neutrino-less double beta decay. I have some nucleus and I need to sum over 2 photon graphs. That means that, when I cut this, I have to sum over a whole set of final states, intermediate states that are all spaced like, 100 keV type thing. The nuclear physics is really complicated here. And so a bunch of people do it, and the bounds on the nuclear matrix elements are like factor of 5. They can't decide on the... So that most of that uncertainty is built into this picture. And so we find that we get a nice little band here. You can sort of already guess the slope. If dimension 5 was flat, then dimension 7 is down by 2 powers on this graph. This vertical line here, that's the Lett bound. If our baryons were any lighter, then the associated pions could easily be produced, pair produced, and have been seen by Lett. So that sets this bound. And we assume that, okay, given a pion mass, how light can the baryon be? It has to be, I guess, 2 times for SU4. It has to be at least twice as heavy as the pion. And so we can fit in this window. This width of this band is the matrix uncertainty, and then you can see that this just extends forever. So there's no reason why in this particular model it couldn't be a TV or a few TV, but it'd be totally unobservable. Because what happens when you hit to this dotted line, in direct detection experiments, that's when they start to see the neutrinos that we know are already there. Eventually, the detector will get big enough, and they'll look long enough that they'll start to see neutrinos coming from the universe scattering in their detector, and they won't be able to distinguish them from dark matter particles. So this is called the irreducible neutrino background. And so eventually, they'll hit it. And when they hit it, then you'll never see this particle. That's why we call it stealth. Unless you happen to tune the target nucleus in some way that it has a huge enhancement to a cross-section like this. Okay, good, almost done. And because nobody knows how to calculate these matrix elements, that's a problem. Okay, so let me finish. Dark matter, constituents can carry electroweak charges and therefore interact with the standard model, and yet still be undetectable. And in principle, undetectable in any direct detection experiment. I should say they could be detected at the LHC because you know, even if you have these heavy charged pions, if you can interact with the standard model, eventually you'll pair produce these things at the LHC. So in a model like this, you could have charged states, charged composite states that are observable. And so we're working right now on the calculations of detection signatures at the LHC. You don't need any new forces beyond a new confining force, whatever it is. The abundances could either arise through symmetric thermal freeze-out or through some asymmetric dark baryogenesis. Future experiments like LZ will eventually rule out dark baryons with magnetic moments, and they even can push beyond this Minkowski bound. Dark matter around a GV is interesting if you can figure out how to make it interact with the standard model. Of course, it's still logically possible you could have this blue ball flying around and it doesn't interact with the standard model at all. That's a possibility. And I think we need to work harder to inform the broad dark matter community about all our exciting lattice results, because you know somehow we are crammed into this tiny little corner. Okay, thanks.
Thank you, and we have a few minutes for questions, comments.
Okay.
If you think in terms of more fundamental theories, there is not much room for SUN if you come from string theory. I think what string theory phenomenology wants to have is a Z prime particle. They have some arguments for that. So
Right.
I don't know. We could propose more and more groups and more heavy particles, but and fix everything because we have enough.
Yeah, I would say most of this hinges on before you see anything, you know, maybe you appeal to arguments like that, but I would just add as a counterexample the 750 GeV diphoton bump, which I'm going to check in a few minutes to see whether it still exists or not as soon as ICHEP starts going in Chicago. Today is the first day. You know, people were quite willing to throw high principles out and say, it's just some new pi naught of some strong sector that has nothing to do with anything, as long as it can produce the right kind of bump signature that you can see. So I think the point is that there are nice, well-motivated ideas like, let's say, the WIMP miracle. And for a long time, when people talk dark particle, dark matter, they only thought of WIMPs. And then once the results from the direct detection experiments kept really pushing and pushing and pushing and not saying anything, and then combine that with the LHC, that we don't see any supersymmetry immediately at the LHC, now everything's wide open in dark matter. People are writing all kinds of models. Because we know it exists, it's there, it has mass, and now the standard, principled explanation of the SUSY WIMP miracle is out the window. So some people are still hanging on, but now before when I talk to people about these kind of ideas for dark matter, we say, we don't need that. We have SUSY WIMPs. But now everybody at least is willing to listen. So
yeah, some quick question.
Well, because of the proliferation now of models that might possible, because the simple ones are getting excluded, experimental searches for beyond standard model physics try to focus on model-independent approaches, where they don't really search for a particular signal predicted by a model, but just for generically for higher dimension operator effects and stuff like that. Is there any hope of doing something like that on the lattice, or will you always be constrained to testing specific models?
Well, I mean, one of the reasons why we're doing this study is actually not to try and test a specific model. But for example, maybe we'll do a range of number of flavors, or we'll look at different gauge groups, and we'll try to see which patterns are more or less generic. And quite a bit we see that there are patterns that just sort of repeat, like things like the ratio of the vector mass to F pi is 8 within 5% in just about every model that we've looked at. The phenomenology like vector meson dominance appears to hold in just about every confining model that we've looked at, although we don't really know why. There are many, the ratio of the proton to the vector mass and light quark limit tends to be very easily predicted by something like quark model or, this kind of thing. These features are very generic, and then they help us inform the experimentalists about what kind of signatures to look for. The signatures are very easy. It's like find this diphoton bump, or find the 2TV diboson resonance, or find pair, charged particle pair production. It's so those things are all in the pipeline. Have always been there. It's just they have to see something now. So we're all desperately waiting for them to see a new particle, and then and they're doing that. It's not like SUSY where you have very complicated decays. These are not complicated. These are simple. You just find a bump, and
All right. Let's thank George again.